Welcome to the final session of our symposium. It's my great pleasure to introduce to you and to announce Professor Dieter Schmalstieg, who is currently a professor at TU Graz. And I just learned that he and Milena Savic, our SP9 project leader, have never met before. So also TU Graz is a huge university. Yes, Dieter is heading the Institute of Visual Computing and something.
Computer graphics and
Computer graphics and visual computing at TU Graz. And also Dieter was my unofficial advisor for my PhD thesis, so he was always one generation ahead of me. So he, when I did my master thesis, when I started my studies, he just finished. He had finished his master. When I did my master, he had his PhD, and when I had my PhD, he had his habilitation and so on. And he's a famous researcher in virtual and augmented reality. So he published gazillions of papers with even more gazillions of references to those papers, and as a result won many awards like the IEEE Technical Achievement Award, which is quite a thing that you only get if you're really one very famous person in the community in IEEE virtual reality. And so I'm very happy that he agreed to come here to his alma mater, basically, because all of these things like PhD and habilitation, and so he did in our institute back then. And yes, so I'm very much looking forward to hear Dieter speaking about topics that are about virtual reality, but also related to the topics we are here, architecture and architectural design.
Thank you, Michael. Thank you for the kind words. Making this connection is actually maybe slightly challenging. So let's see, who has some experience with augmented reality here in this audience? Some idea of what it is. So maybe that's half. Yeah, I mean, given that you're a relatively, technically oriented audience, this is fine, of course. So I've been doing augmented reality and virtual reality for many years now, over 20 years. And today I saw mostly work on, which of course I can relate to, but it's mostly on geometry and design. It's a slightly different sort of area of the playfield. So the question becomes, how is augmented reality relevant? So I took the opportunity of capturing Michi while he was giving the introduction. I apologize for the blurry photograph that I made, but this is basically saying it. So there's this design that we've mostly heard about today, and great work. My congratulations to all the speakers before me. There's also AEC, which is this more technically oriented part, architecture, engineering, construction, maybe more even on the engineering and construction part, which is getting increasingly digital. And this is pretty much what this picture here is showing. So my interest is part of my interest is in augmented reality, so that's on the ICT side, of course. It's interface technology, and we do this because we want to bridge with various disciplines, and AEC happens to be one of them, where I believe it's quite fruitful. And my talk today is about some examples of work that we've been doing using primarily augmented reality for applications and problems that happen in conjunction with the built world. I'm not calling this AEC, but some of it probably is. So, like I said, this goes way back, and I like to start by showing super pixelated videos because I'm pretty much the only person on the planet who has kept them. There's not too many of these 320 times 240 resolution videos that we made in a teeny tiny lab of about 10, 12 square meters that we had at the time, showing actually 25 years ago the world's first collaborative augmented reality system. In this case, showing some mathematical functions here which are being inspected and interpreted by our test subjects. Now it's 25 years later. What is the difference between then and VR research goes back even a couple of years earlier? Well, today I can go to the store and buy an Oculus Quest 2 headset for 350 euros, and it's pretty damn good. That's something that we didn't have 25 years ago when we spent a lot of money on very, very poor hardware quality. And unsurprisingly, if you look at the number of papers that are being published, that in this case in the visualization community, it goes up. So visualization using virtual and augmented reality rather than conventional desktop-based interfaces is now peaking. And you see how clearly the availability of the hardware has enabled all the labs must have one, and now all the visualization labs also publish VR papers and AR papers. But that also means, to paraphrase, that it's very easy to get started in immersive visualization. Using this new media is now accessible to everybody who's interested in creating and presenting visual artifacts, and this is precisely what we're going to talk about. The question is usually asked, this is not my work, this is work by Maxime Corday and his collaborators. Data visualization is now coming to virtual reality, then it's called immersive visualization. And that has a number of substantial benefits. If you want to show very complicated things, you get increased spatial understanding, you get decreased information clutter, you get peripheral awareness because the field of view is just so much wider. Higher information bandwidths, you can leverage spatial memory, and the positive effects of that have been demonstrated for a variety of disciplines now. Of course, here I'm mentioning mostly something from the domain of information visualization, so that is abstract data like sports data or stock data or other measurements. But the whole thing, of course, is equally relevant if the data has a special meaning, such as a building model. And this is what we've heard a lot about today. Now, going forward, this is just virtual reality, right? You are sort of transported to an entirely artificial environment, which has really interesting use cases. But I primarily want to talk today about augmented reality devices, such as the Microsoft HoloLens here. This is not 350, it's more like 3,500 euros. Maybe it's slightly cheaper now. But it also gives really solid performance, although it's technically, I would say, there's always a decade that augmented reality hardware is lagging behind virtual reality hardware because it's just so much harder to do. But this thing is really impressive. This is it's just an example. Apple will come out with its own flavor maybe next year, they say. It's a see-through display, so this is why it's augmented reality, right? You see not only the three-dimensional computer-generated graphics, but you also see the real world at the same time. And the two are blended together, and we're going to see how important that is throughout this talk. The second thing is this is nicely engineered, it's self-contained, it tracks itself in 3D, in continuously, without a lot of problems. And it has a built-in complete computer, so it's just an Android device. The operating system looks like your phone, right? And if you're building interactive applications, as people generally do, I've seen a Unity demo just in the shop floor out there. This is the same thing that we're doing here. On devices like the HoloLens, but you might also use an iPad. The iPad is also a pretty powerful device. And what do you get? Well, I mean, look at this example here. This is a machine. Well, it's not really a machine. It's something that we built from scrap parts because we couldn't show the automotive company that we're working with won't let us show their real machines, so I have to show this machine. What you see here is that you see, for example, the flow of gases in this machine superimposed in 3D, and it tells you something about the state of that machine. Yeah? So I would call that engineering, an engineering application. And it already tells you what situated visualization is. So the key characteristic of a situated visualization is threefold. The data is related to the physical context around us, that is reality around us. This is why it's augmented reality, because it's referring to the physical aspects, the real aspects of the environment. The visualization is based on relevance of the data to the physical context, and the display/presentation is also placed in the physical context. Yeah, so we're firmly anchored in this physical context. The physical context now, again, is a term that describes a collection of things. And it's mostly about the location where the user is, the objects that are at that location, the location of the objects, if the objects can actually move. You can extend that to include people, and other aspects such as time of day, lighting conditions, whether you're indoors or outdoors, what your objective is, and so on. All of that also comes into play. Yeah? So these are things that will shape the user interface that we want to deliver with augmented reality, and we call this type of user interface situated visualization, because it is a visualization that is not detached on your screen, but it's a visualization that is delivered right at the task location. Yeah? And since we spend most of our time away from the desktop computer, I mean, of course, not if you're doing your office work, but if you think about somebody whose job or interest it is actually to go to places and fix things, they don't like to go to the desktop computer to look something up. They want it to be delivered right there. And this is what we're trying to do, to make visualization useful at the task location. And this is more than mobile visualization. You can have, you can take a desktop visualization, and then on your smartphone you get the same thing, only smaller. Well, I mean, I need glasses now. My kids stare at their smartphone screen all day long. They will need glasses too. But the point is that a minified desktop visualization on a smartphone is not going to have the same kind of usefulness for the application purpose that the augmented reality visualization that I'm describing here will have. So that's the one thing. The other part of my title is, of course, the digital twin. Augmented reality meets the digital twin. The digital twin is, let's say, a data repository in the way I define it, that captures this physical context that we were talking about. Yeah? So how does the application know what to show, what makes sense? Well, we have to store it and process it somewhere, and this thing we call a digital twin. If you actually go to relevant sources such as Wikipedia, you find very interesting descriptions. They're very vague. This is a very broad term. This is not a scientific term, in my opinion. It's a marketing term somehow, but it certainly encompasses a broad variety of aspects, such as spatial data and non-spatial data. And if we consider the built world, then the spatial data is obviously the model data, the computer-aided design data that you may have about the physical world. The non-spatial data may be, it was a brief discussion earlier today, the function of the building, such as ventilation or electricity or something like that. Yeah? And of course, we are interested in both together. If you're an electrician on a construction site, you want to know whether that plug or that cable should go there or not. It's both a spatial and a non-spatial problem at the same time. Likewise, this digital twin data can be non-varying. That means just static, like you build a house and you have you design a house and then that model sits on your computer, basically. But we all know if the house actually gets built, it slightly deviates from what was planned. And there are other things such as, I don't know, flood data or renovation data that continuously change. Yeah, so many problems have also a temporal dimension. then the next point is, where does the data come from? Does it come from scanning, from modeling, from simulation, from inference, if it's more a artificial intelligence kind of problem? Is the data pre-computed, or does it come in streaming, so I really have to capture it on the fly? This is particularly relevant when it comes to sensor data. And since buildings are increasingly becoming smart buildings, there's lots of sensors that should interest us. So all of these questions inform us what we can store about reality in the form of a digital twin. And now we're going to try to also put that to use by delivering situated visualizations on that. We can deliver visualizations about digital twins everywhere. On the desktop, for example, that's probably 99% of today's use cases. We can do it immersively. You might inspect it in a virtual reality, but I am specifically interested in an augmented reality, situated context. And what we want to do with it is we want to become smarter. We want to make sense of the situation, of the physical and the artificial situation combined. And I'll give you two examples, starting with one that is about subsurface utility engineering. So here we're going to talk about information that relates to, all the infrastructure buried in the ground, such as gas pipes and electricity and so on. And this is an important problem. These data sets are stored in, geographic information systems. This is on a slightly larger scale than what is probably done for architecture. And if somebody wants, for example, to dig up the ground for a construction project, they need to get informed. There's legal and governmental regulations about that. They need to be informed about the status of the underground infrastructure. Also, if you want to repair something, if there's an outage of sorts or whatever, then you better have the right kind of information. And you must have it on the task location. And what they do today is they bring a laptop with a geographic information system, and then the boss man of the construction workers is looking up stuff on the laptop or maybe on a tablet. So this data is clearly slowly varying. It comes from scanning and from modeling, and we want to show it at the task location. We've done that already quite some time ago. So I dug up some pictures from 2009 showing infrastructure before excavating. And I'll play that little video for you. That is actual data from Cambridge at the Cambridge location. Look, the cars are driving on the left side of the road. You also see these gas and electricity lines superimposed and color-coded. That ran on, so this is not all the same application, but you see we had PC tablets at the time which were not quite handy, but you've seen something like a precursor to Microsoft Surface. Yeah? And the kind of visualization styles that you see here, just overlaying the graphics isn't, of course, very helpful because it appears as if the pipes are floating above ground, so you rather want to have a view that looks as if you've actually dug a trench, which requires some additional graphics routines to do that sort of thing. But all in all, these people working in subsurface utility engineering weren't super happy with the user experience around 2009. Yeah? So this is my own work, but I'm showing it as a sort of a poor example where we were maybe too ambitious. I mean, it was still cool to do it, but the truth is the people who work in subsurface utility engineering are very cost and time conscious, and if you can't persuade them that they're actually going to save time with your technology, they're not willing to try anything. Super conservative industry. But today's commercial products, this is sold today for lots of money by companies such as Trimble and makers of theodolites, looks very much like what we've done back then. So they haven't advanced, but we weren't happy with that, and so we made a new attempt. And one of the things is always this positioning problem. outdoor positioning is notoriously difficult. If you use, I mean, now you're going to say, well, I have GPS in my smartphone, and that's true, and Google Maps works very nice, but try using Google Maps and drive off the highway. What does it do? It shows you staying on the highway until you're about 200 meters off the highway, because then it realizes, well, the measurement that I'm making is not, you know, agreeing with the road prior that I'm using here, that this guy is going fast in a straight line. So now I'm going to make a correction. So this is why these map services work, because on a relatively coarse scale, they work with some tricks that mostly have to do with derivatives, right? But you can get super accurate GPS, and that's what the surveyors are using. But they use equipment that costs 10,000 euros, and they come and do like the surveying of your lot or something like this. The cheap GPS chips in the mobile devices can't do that. But you can buy just the chips, and this is what you see here on the right-hand side. We've built a little device. We don't usually make hardware, but we built a device with a real-time kinematics differential GPS and some other embellishments that is very cheap, and it talks via Wi-Fi with an arbitrary device of your choosing. So if you glue it to the back of an iPad, then you get an augmented, you know, a really nicely engineered tablet capable of delivering augmented reality with self-tracking and all, even with scanning ability, because the iPad has a LiDAR scanner, plus the global positioning. That gives a really nice result. So what this is actually doing is what all the augmented reality systems are technically implementing is shown in blue on the left-hand side here. It's a multi-threaded sort of localization approach that consists of tracking and mapping. The mapping is the scanning of the environment, where you get the point cloud of the environment, and the tracking is where they find the pose that the camera has relative to the scanned environment, and that must be very fast. That must run at 60 hertz if you have a 60 hertz display. Yeah? Commercial implementations of this technique called SLAM, simultaneous localization and mapping, are now in the Apple iPad, in the HoloLens, in the Oculus Quest. All these devices that do self-tracking do it in that way. But what we added is this green part, this really fancy miniaturized GPS, and it upgrades the local pose only relative to the starting point where the scanning started to a global pose. And now you can go back to a database such as a geographic information system and retrieve the information about the pipes and such stuff and show it in the augmented reality visualization. And then on top of that, we said we don't want to do artificial pipes anymore, like, you know, computer graphic cylinders. We want to do what they're actually doing in the field, such as virtual spray paint simulation. And this is what is shown here. So the LiDAR of the iPad scans the ground, and then we paint little colored dots with computer graphics on the video, on the textured, well, on the textured mesh actually that comes from the scanner, from the iPad scanner, for example. And with this virtual spray paint simulation, you get really, really nice results. What you see here on the left-hand side is what they do in the real world, and on the right-hand side, if you look at, for example, this orange marking here, that's virtual. And it's following the ground precisely, including the height difference when you go from the street to the pedestrian walkway. And the advantage of that is not only do you not make the ground dirty and have to remove it after construction completes, but it's also a completely digital data set that can be taken home. You can inspect it in the office and do any other kind of work with it. And the second application that runs on the same system is virtual daylighting. So the best documentation is always an actual documentation of what happened. So when they dig up the ground, they take 3D scans already, and they put them in their database, but then, of course, the next construction worker probably won't have access to that data set, and it's not presented in the context of the road that is, again, dig up. But what we can do is, before they actually dig up, we can superimpose what we know was already there. So here, of course, what you see on the left-hand side is a picture of after the ground was filled again, but we can go out, and this is what is shown on the right-hand side, and allow you to look with a simulated X-ray vision like Superman into the ground and reveal how it looked like before they covered it up. And here's the thing for real. So this is the captured video, and this is now after the ground has been closed, as you can see here. And I think the visual quality is very convincing. At least our collaborators were happy with that. Right, so the second example that I wanted to talk about is a machine room in the basement, Heizungskeller. Yeah? Like I said, a digital twin can be many things. Assume that you have a modern basement where sensors have been installed with all the heating and water and so on utilities. You probably have that anyway. A smart meter is just a computerized power meter. And when maintenance goes on, it would be very interesting to tap into this whole sensor infrastructure. And if you think about larger smart buildings or factories, so there's going to be thousands and tens of thousands of sensors and sources of information. Yeah? And now we want to deliver this information in a situated manner. And I'll just explain the scenario a little bit. Let's assume you have heating or water installations and so on, always Internet of Things. So these sensors are constantly communicating information. Only what would you do with that information? What happens now in the factories that they have a control room where all the sensor data is collected, and there you have a visualization application running, helping some supervisor to make informed decisions. But then when they go out to the shop floor, that information is largely unavailable, or at best you can take it with you on a whatever, tablet computer or something like this, if that works at all. But we want to present this data in the physical context. So assume you have computer-aided design models of the environment or maybe the 3D scans. We want to automatically deploy these 3D models. We want to combine them with the sensors that are actually there and live, which isn't the same as something that may be, planned. There may be a plan to put a lot of sensors into action, but half of them may be broken. So you want the real-time situation, and we want visualizations to be generated automatically, of course, based on some preferences that the user has expressed at some point on the data, on the sensors that exist, where the sensors are or where the machines are that the sensors are attached to. And everything should be as automated as possible, because certainly if you make the facility manager go into the basement to fix some electricity problem, this person doesn't want to resort to complicated JavaScripting or whatever in order to get the sensor data out. That's not how that is helpful. Also, we wanted the whole interface to be adaptive. We call it semantic level of detail. That means you go closer to a facility and you get more details on where you're looking and less details where you're not looking. And this could look like here in the picture. This is our actual basement in our institute in Graz, except that we manually place the sensors there, right? So we do not have access to the actual building infrastructure. We just put our own running but not meaningful infrastructure. There are lots of thermometers because we had them in the cupboard somewhere. And then you get these visualizations that show you information about what's going on, and the red-green stuff, this is some temperature curve, only that it's not very elaborate here. But the main point about this example is that from a digital twin perspective, the machine room is now a very compelling example. It's it's sort of real time. You know, the construction site is only changing every year or so. The temperature in the machine room changes all the time, and the fine granularity. This machine is too hot, this machine not. So automatic means the visualization must really be aware to the detailed physical context. The situation is different, both in space. Every basement will have an entirely different configuration, yet that should run anyway. You don't want a bespoke application development for your basement. That would be not economical. There's also a different situation in time as different equipment is used in the basement at different times. In the winter you switch on the heating, in the summer not, and so on. Or something may be broken and other things not. So all static configuration, and this is how most visualization applications work. Static configurations are not good. You cannot expect that you have a data set that you just load at the beginning and it solves your problem. Instead, the visualizations must be reactive to the context. Technically, that hints at what is called in computer science the paradigm of event-driven functional reactive programming, but I assume that's not for most of this audience here, so I'm happy to discuss it with anybody who wants to know more. I'll just give you a hopefully reasonably intuitive overview. So we've worked on the software infrastructure, something I enjoy very much, that is very, very versatile. The point here is that the data, in order to arrive at this situated visualization, the data needs to go through 4 stages, which are actually the typical stages that all visualization applications have, only in a very, very modified, runtime environment here. The first, of course, is the data sources. So these data sources are not manually collected, but they come from all these sensors. So what we do is we scan for all the sensors that are on the network, and the Internet of Things people do a marvelous job at that. There's frameworks such as message queue telemetry transport, MQTT, that automate many of these kind of problems. So point 1 is where we connect the Internet of Things devices. And then they go into a software environment which also comes from the Internet of Things world, called Node-RED, where the data is processed and stored. See that little box saying databases there? So depending on who I talk to, this may or may not be interesting, but of course there's a lot of sophistication in databases. This is existing technology. Only visualization software is often not able to tap into it, and virtual reality, augmented reality frameworks know nothing of databases. So suddenly we add a database, but we do it in a way that comes from an industry that uses databases, which is the Internet of Things industry in this case. And I'll say no more about that, but of course databases are powerful. So this is how we can process and filter the data. And then we leave this sort of back-end infrastructure, which is usually like, let's call it an edge server, the server that sits in your building. And we get to the actual augmented reality device that's on the right-hand side here. And there's also a software stack on the right-hand side, which is more chosen from typical virtual reality, augmented reality, and game engine software ecosystems, such as Unity, for example. And what we do here is we generate a visual encoding of the data that can be done with, more or less standard graphics tools, and then the whole thing is presented in augmented reality via the toolkits that are already there for running, mostly games on the HoloLens. So the game graphics are repurposed because games sell these headsets, and the game graphics is repurposed for doing visualization, in this case, situated visualization. Now I'll show you what that looks like. So here's my PhD student, Phil, pretending to be a janitor. And he is invoking all these graphics, which are related to the various sensors that have been placed in the environment via these leader lines. And some default graphics is created, and then you can also manipulate these graphics with hand gestures, like now he's just repositioning it. And as he's looking towards the next sensor, that graphics is generated and the others are minimized or removed. So it's a context-sensitive display. It gives you access to all that sensor data, and that would work in any basement that complies to sort of the specifications that we've laid out. That's the point. Yeah? There's nothing hard-coded in this application. It doesn't know how many sensors there are. It doesn't know the types of the sensors. All of that is scanned on the fly. This is the main capability that all these Internet of Things visualization applications, even for the desktop, for the command and control center, that I've seen so far, don't have. Okay. Now, what are we seeking? We're seeking to deploy situated visualization and then analytical capabilities on a large scale, outdoors or indoors, but definitely away from the office, and for lots of data, because this data that we have in digital twins, be it building information systems, geographic information systems, construction information, this is just getting more and more and updated at increasing higher rates. I would say there's an age of big data now also in the AEC field or in the built environment. And the people who deal with these data collections want to form digital twins. My argument here is that also lends itself to AR, and we can make working systems now that deliver context-dependent visualizations via augmented reality at a task location anywhere in the built environment. There's still a lot of work to be done. This is what the researchers like myself do, the interfaces that should be used for query and manipulation of these data, but the need is clearly there. This is a conceptual image here showing a flow visualization of some basically airflow around the building. That's also something that is being computed, but it's not shown on the actual building outdoors, so maybe that's one of the future projects. And with that, I would like to conclude. Thank you very much for your interest. I'm happy to take your questions.
So thank you for this talk that shows that the interfaces are really very important as well, and I think also in architecture and building this can be very, very interesting for us. Are there any questions so far? Yes, over there.
I have a couple, but I'll only ask one. And I'm a computer scientist, so I am interested in the details, but leave that aside. I'm curious about the use of a digital twin without walking around a building. So imagine having a digital twin of a building and then an earthquake hits, and it's not safe for a structural engineer to go in. Have you thought about that application, and how would it work?
Oh yes, I suppose. I mean, obviously I talked about immersive visualization in the beginning that would use a virtual reality system to deliver this information, and that could replace a command and control center with just large text screens or something like that. If you think about disaster management, letting the coordinator get a spatial understanding of the situation that is remote is definitely an important area of application as well.
Just to follow up, I'm thinking about a situation where a building is under stress, and maybe the structural units are under stress after an earthquake. Could you integrate not just the before picture of what it looked like, but what it may look like under the building skin based on sensor data that could show, the fast acceleration that a particular joint?
You can definitely do that, and you could do it in situ or in a sort of telepresence situation. Both make sense. Yeah? One of the important ideas is that you show abstract data, such as, for example, a heat map representation of some data distribution. Yeah, temperature can be encoded, red is hot, blue is cold. Yeah, we all know that. So you put that on a surface, you've all seen thermal scans. Yeah, so you simulate a thermal scan from individual measurements or from whatever source you have. And there are many other ways how abstract information can sort of be blended with our perception of the real environment. I think this is what you're getting at, and augmented reality in situ is one important class of using this, but of course there are others. The general idea is independent of the type of display that you're using.
Thank you very much for your presentation. I work in the area of digital twins, and you already spoke about big data. So digital twins are normally extremely data heavy. And I was thinking of an example of a maintenance situation in a basement where there are, let's say, 100 electrical cables, and I need to switch out just one. Do you have any strategies for eliminating visual clutter? For example, when I look at those 100 cables that are very close to each other, are there any strategies how I can orient myself and not get lost?
Yes, there are strategies, but you have to carefully define the problem. Yeah, it's very hard to make a general purpose solution for that. Generally, you go through a series of filter steps. I mean, this is what everybody on the desktop also does. If you load a big data set, you just see, a hairball. That's the typical, that's how visualization people, I'm looking at Edi Gröller here, explain in their lecture how bad visualization looks like. And then you take countermeasures, like letting the user specify directly or indirectly filtering criteria, use, like I mentioned, if you're actually moving around, you can have proxemics, right? You choose where to look and where to go close, and this is already an input, like a way of specifying what your interest is. Of course, when you come to two cables that are 1 millimeter apart, that the tracking precision may already come to a limit, maybe pushed to a limit, and I don't have answers for all these problems. But in general, I think if you know what you're trying to visualize, then one can take existing design knowledge from the visualization domain and just apply it. The problem becomes if it's exploratory and you don't know what your interest is, and also the environment is only partially modeled. That's another big problem that we're having here that desktop people don't have, because they always have white pixels in the background. Then it gets harder. So I think this is one of the grand research challenges. I have some ideas based on basically patterns, what people like to see. So at least with minimal effort, something will be arranged for you that is sort of digestible, which I believe can work. But you will have to ask me about that in a couple of years. It's not there yet.
Thank you.
I think what was very impressive is this image you showed, how you can look at the pipes, how they were before. But I think very often, I mean, this assumes you have a 3D scan. And I don't know how often that is really done. I think in reality you often have incomplete data, missing documentation, and so on. But you still might know where the pipe actually is fairly accurately. So I saw at the beginning you had a slide where you showed a very simple visualization of a trench and so on, but could you augment that to make, even without having these 3D scans, similarly highly
Well, I mean, this is what I tried to convey. We did that in the past, and the data quality is just poor. Right? And if you're too aggressive about interpreting the data that is partially incomplete and so on, you end up misrepresenting what's actually there. So that's dangerous. Yeah? A lot of the existing underground infrastructure will say the gas pipe is on the left side of the road. Yeah? The scans, the better companies do the scans regularly. So whenever they dig something up, they have this scan. It's only that they can't access it in a way that they do it for documentation purposes and for liability purposes, which means it's just a data grave, right? The data graveyard. And we're trying to make better use of that, assuming that nobody stealthily modified the underground infrastructure in between. It's probably a good representation of what is actually there, provided that the operator has been doing this for 10 years and has scanned everything. So this is a chicken-egg problem. That building the digital twin requires collecting the data, and before it pays off, collecting the data may not be economically justified. And here we're trying to opportunistically use some trend, let's say. I think it's a good solution for this particular situation, but of course not for every other possible kind of use case.
You were also talking about the software stacks, and if I look at here this audience, what is very frequently used is BIM models. And probably if you want to have visualizations in situ, you would probably go back to a BIM model, for example, looking for pipes and so on. I mean, I guess this would probably also complicate this software representation that you had there. Have you tried?
I did not talk about any data formats that are actually in that database, in particular the static ones. We fill in whatever we can find. The main idea here is, so maybe I'm selling this to the wrong audience, I'm not sure. The main idea is that people who build VR and AR applications think like game designers, which means they have a level, there's a big file on disk that has some content, not a database. They don't do things like make a query of give me all the pipes. That's already a fundamental paradigm shift for VR, AR software development to do that kind of thing, where you have a sort of a query-oriented retrieval. It may be common in information systems and information visualization systems, or let's say more common, but they typically don't have this, in the V's of the big data, the velocity, the streaming data that comes in at a high rate. So now we have it all together. We want to deliver it on a platform that doesn't do databases. Data has high velocity, and it has high volume if it's a building information model, for example. That is still, I mean, just putting that together is still challenging, but I'm just trying to raise some awareness there that you're really going to need all these things. If you leave one out, you're not going to have a convincing use case.
Okay, any more questions? Otherwise, Dieter, thank you again for the presentation.
Thank you. Thanks for having me.